Hi everyone, welcome back. We are going to continue on with day 2 of 7.3, Vectors in the Plane. The essential questions are how do I perform basic vector operations and find the unit vector. So we're going to be working with some very basic vector operations, including addition, subtraction, and multiplication. And we're also going to be finding something called the unit vector, which I will explain further in just a moment. All right? So you don't need to write this down, but let's go ahead and take a preview in the book real quick. So the two operations that we're going to look at are called scalar multiplication and vector addition. So addition and subtraction are going to refer to how we shift the vectors, or basically build upon one vector. Let me shift it up right here. So you start off with one vector, and then you add another vector, and it creates an even bigger vector going in a certain direction. Then over here in this little diagram, they show the effects of what would happen if we multiplied a vector by a certain value. So for example, multiplying a vector in half will cut it in half. Multiplying it by 2 will double the magnitude of the entire vector. And then multiplying by a negative, it's going to go in the different direction. So all of these number and operations that we're going to be using on vectors do affect the actual graph of it, and we're going to show the graphs as well. Okay? So the first thing I need you guys to copy down is the definition of vector addition and scalar multiplication. Pretty simple, pretty basic, but let's go ahead and write those in and practice them in the next example. All right, so let's move on now. In example 1, what we're going to do is both vector addition and some scalar multiplication. I'm going to combine both of them together, and we'll see how it affects the graph of it. Okay, so not examine, example 1. We're going to say let vector w. I'm going to try to make it as bold as I can. Remember, you got to make it lowercase and bold. Let vector w be represented by 3, -2, and vector v as 1, 4. Now remember, when we write it in this form, we're talking about the component form. In other words, the vector stemming from the origin. Okay? So let's go ahead and start off with the first example of of example 1, so letter A. We'll have vector w plus 2 times vector v. Okay? So how you're going to write it out is basically you substitute each vector with its component form. So w will become 3, -2, then plus 2 times the other vector, so 1, 4. Right, so simple enough, we're just substituting in. Here, I'm going to distribute the 2. And I am showing all of the work, but you don't need to necessarily do all that. Just want to make sure that we understand what's going on. 2 times 4, right there. And then, simplifying further, 3, -2, plus 2, 8. And now the way the addition is going to work is that we only add the first number with the first number, and then the second number with the second number. So our resulting vector, the component form of it, will be at 5, 6. Okay? And what I've just found here is the component form of the resulting vector after we add these two vectors up here. And let's go ahead and sketch in the graph to make it kind of more obvious as to what's actually happening. So, drawing a big coordinate grid. First off, I'm going to start at 0, 0. That's my initial point. And the vector that I started off with was vector w. It went to the right 3 and then up 2. So 1, 2, 3, 1, 2. Okay. Actually, hold on. Sorry. -2, so it should be going down. My mistake. And then it's going to be going in this direction. So southeast. And that's going to be vector W. Now we're adding 2 times vector V. Vector V normally just goes 1, 4, but I'm going to double that. So to the right, I'm going to go 2 units, 1, 2, and then the 4 tells me to go up, but then I'm multiplying by 2, so I'm going to go up 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so continuing from where we terminated, this now becomes our new initial. Draw in your directed line segment, and that's going to be vector V. Right? And the resulting vector from the origin is this one. This vector is vector W plus 2 times vector V. And if we actually check the coordinates, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, that's actually the same exact spot as what we calculated, 5, 6. All right? So that's the whole idea of vector addition and scalar multiplication. We're representing the change and what's happening in terms of our vectors and the resulting vectors. Okay? Let's go ahead and practice one more. This time I'm going to run through it a lot quicker. And it will involve subtraction this time, so we will be moving slightly differently. So we start off 1, 4 minus 3, negative 2. So which means I'm going to have 1, 4 minus, or actually plus, negative 3 and positive 2. So my resulting vector is going to be at negative 2, positive 6. Sketching it in. All right, so starting off at vector V from the origin, 0, 0, my initial. Going to the right one, 1, 2, 3, 4, up 4. And that's going to be vector V. And then for W, I'm subtracting. So now I'm going to basically add the opposite. So adding on a negative 3, I'm going to go to the left 3. 1, 2, 3, and then up 2. 1, 2. So there's my negative W vector. And the resulting vector is from the origin all the way up here. This vector represents vector V minus vector W. All right, so vector addition, subtraction, scalar multiplication, and the graphing all combined. That's part 1. Hopefully it made sense. Very simple math and just some graphing in addition to it. Okay? The next part will also be fairly simple. What we're going to be calculating is called the unit vector. Before we do that, I do want to show you, in the book, they show you the properties of vector addition and scalar multiplication. A lot of it is very similar to all of the properties that we know in Algebra 1. So commutative, additive, inverse, all those things, they apply here as well. So you may write that in, but it's really just the idea that the properties carry over in this case. Okay? So on to the unit vector. And the unit vector is a vector kind of modified from one of these guys, but it will have a magnitude of 1. Having a magnitude of 1 makes things a lot easier if we were supposed to say, oh, you know, let's give me a magnitude 5 vector from this. If I had to actually calculate the magnitude of this, this might come out to like 3.4 or something, and changing that to a magnitude 5 vector could be more difficult. Changing this to a magnitude of 1, however, would allow me to just multiply what I had by 5 and make things a lot simpler. So what we're going to do now is calculate the unit vector, and we're going to prove real quick also that what we just found is equal to 1. Again, the magnitude of 1 will help us out later on when we're asked to find bigger magnitudes and we don't want to work with such complicated figures. Okay, so the unit vector will be very useful. Let's go ahead and start. What I want you guys to first copy down is what a unit vector is. It's not highlighted in yellow, but I do want you to write u equals unit vector. And it's going to be equal to a vector divided by the magnitude of the vector. This and this are the same exact thing. What they're just trying to show here is that you're multiplying a vector by the reciprocal of its magnitude. Okay? And that's just to make the math look a little bit cleaner. But let's go ahead and try that out first. So example 2, find the unit vector. All right, so if I'm given a vector v is equal to 4, -1, that being its component form, I'm going to go ahead and first find the magnitude, okay? So the magnitude of v. And the way I know the initial point is that because this is written in component form, I know it starts at the origin. So really I'm just going to use the distance formula with the origin, okay? So square root of 4, that's the x value, minus 0 squared plus y, actually -1, sorry, minus 0 squared. That's equal to 4 squared plus -1 squared, square root of 16 plus 1. And we get a magnitude of the square root of 17. Not a pretty magnitude to work with, especially when we need to modify it later on and get a magnitude of 2, 3, 4, or 5, something like that. So we're going to convert what vector we have right now into a component form that has a magnitude of 1. The way we're going to do that is we're going to divide our vector, vector v, by its magnitude. Now again, you could combine all these steps together. I just want to show each piece individually. Right here, vector v is 4, -1, just like written above. And then the magnitude is going to be the square root of 17. Okay? So what happens here is that each one of these parts in the component are going to be multiplied by 1 over the square root of 17. And that's what they meant earlier by that notation. So I'm going to distribute it. And my new component form will be 4 over the square root of 17, comma, -1 square root of 17. And because we are supposed to rationalize it, I'm going to multiply the top and bottom of each one by the square root of 17. So I have 4 square root of 17 over 17, comma, negative square root of 17 over 17. Right? So that would be the component form of my unit vector. If you find the magnitude of this component form, so in other words, I'm going to do this -0 squared, this -0 squared, and I do all of that math using the distance formula, my answer, the magnitude for this guy, should be 1. And that is the unit vector. Okay? So you may prove it to yourself. Otherwise, go ahead and move on to the Google Forms. If you have any questions, write them down, and we will see you tomorrow.